Hi, we are the University of Massachusetts-Dartmouth team for the Beyond 5G Challenge. Our project was on researching an autonomous jammer classifier in real time using incremental learning. The scope of this project includes machine learning in wireless systems, jammer implementation and classification, as well as online, real-time incremental learning. Our goal was to leverage the flexibility of SDR to create an adaptable jammer classifier capable of learning in the field autonomously. Incremental learning allowed us to take a standard convolutional neural network and introduce new classes in the field. Current research has shown that it is possible to classify jammers in real time using deep learning. This project introduced online incremental learning to jammer classifiers, augmenting them with the ability to adapt to changing environments. Additionally, we developed an incremental learning architecture for signal classification, which we plan to make public. In this video, we will give a live demonstration of this system and show both an offline trained network and the real-time incremental learning. To create our experiment, we used both USRP B210s given by the AFRL. The physical setup can be shown in the image here, where one USRP was used as the transmitter and receiver pair, and the other was used as the jammer. The USRPs allowed the jammer to be reconfigured with different jamming types to simulate multiple jammers on one device. And they also allowed us to analyze received baseband signals on the true receiver so we could detect the presence of jammers and classify them. Ultimately, these two USRPs were used to make 5 different configurations. We use GNU Radio to control these radios and to implement the jammers. Using ZMQ sockets, we were able to leverage Python for more advanced functions by sending and receiving samples from outside the flow graph. My name is Todd Morehouse. I'm an electrical engineering PhD student. I worked on the hardware design in the incremental learning.
I am Charles Montez, and currently am a PhD student in electrical and computer engineering. It's my first year. I worked on the incremental learning part of the project.
My name is Michael Bisbano. I'm an undergraduate electrical and computer engineering student. I worked on the jammer development.
My name is Jingfen Lin. I'm an undergrad electrical and computer engineering student. I work on jammer development.
I'm Dr. Rolling Jill, an assistant professor of electrical and computer engineering department of the University of Massachusetts in Dartmouth. I'm a faculty advisor of the project.
I'm Professor Jiang Wu at Wright State University. I'm a faculty co-advisor of this project.
Okay, so I'm going to give a demo on the real-time learning. So here we are going to have a network that's already been pre-trained on 2 classes. We need some baseline here. And this will be the CNS jammer, so constant noise spot. It's just blasting one band with white Gaussian noise continuously. And then the other one was no jammer present. This jammer is implemented in GNU Radio, so here is the flow graph for that. To start, here is how we generate our transmit wave. So it's just a sine wave, 1 kilohertz, and it's multiplied by a square wave at 5 hertz. That gives us a switch sine wave. And then on the receiver, we receive the baseband samples over the USRP, and then we decimate them by 80 just to reduce the data size, and forward it over ZMQ to our machine learning part. The CNS jammer, it's very straightforward. We just have a white Gaussian noise source that feeds directly into our USRP. So if I run this flow graph here, we'll see all of the transmit and receive and jammer signals. So this top graph here is just the sine wave that we're transmitting. Occasionally it just goes flat. That's when that's the switched part where it switches off. And then we have JX here, which is our jammer transmitter, and it's just white Gaussian noise. And then the receiver's FFT and the received signal. Now, the received signal in FFT is frozen right now. This actually waits for the machine learning ZMQ server to come online so that they can synchronize together. So if I start the detection server, it'll take a bit to turn on. It'll load the model and load up TensorFlow. And now that it's on, it's classifying these samples, and it's classifying them as the class 1. Now this might be meaningless, but since this is an unsupervised classifier, it doesn't actually have the ability to put a label to this. But when we trained this previously, we trained it so that way a class of 1 is the CNS jammer, and a class of 0 is no jammer. So we can see that this is correctly predicting this as a CNS jammer. If I go back into my flow graph here, and I take my jammer gain and set it to 0, that will effectively stop the jammer completely, and we'll just have the true received signal coming across RX. So now we can see on our flow graph that we just have the switch sine wave here. And then in our command prompt, we can see it's now classifying these samples as 0, so no jammer present. Now, if we switch this jammer to either the RAS, the random spot jammer, or the RES, the reactive spot jammer, this classifier is going to detect that the jammer has changed, and it's going to switch into training mode. So I'm going to stop this flow graph and switch to the next jammer. So let's start with the RAS, the random spot jammer. So the goal of this jammer is just to randomly transmit white Gaussian noise for very brief amounts of time. To do this, we use an external Python script. This script will just generate null frames, so no frames with no amplitude, 0 amplitude, but with white Gaussian noise randomly interjected into these frames. So if I start this flow graph, once it's started, we'll see that the command prompt will switch over to detecting. It'll detect immediately. So here it's immediately detected that this is a new jammer type, and it's switched to training mode. So it's going to collect 100 frames to train on. If we look at our flow graph, we can see the RX here is different. If I zoom in on this, we can see that the noise is now at random periods of time, and it's always changing. So as soon as this finishes collecting 100 frames, it's going to take these 100 frames and train on them over 80 epochs. It's using a lot of epochs because 100 frames isn't really that much data, so it takes a long time to actually train to be able to classify these frames accurately. This number could be reduced by a bit, but it would sacrifice accuracy. But it doesn't take too long. You can see we're already almost done with the training. We're on epoch 50, so in a moment we'll be able to classify these RAS samples. Okay, so it's finished, and we can see that now the terminal has showed us tons of samples that it's classified. Those are all the samples from before when it was training. It wasn't classifying, so it's got to go back and classify these new samples received, and it's classifying them as class 2. So again, this doesn't have the ability to label these classes. It just says this is class 2, so the third class that I've learned, and it's able to discriminate between this third class and the other two. Now this just trained on the new samples it received. We didn't send it any more CNS or norm samples, but it's still able to classify these CNS and norm samples. If we switch back to the CNS jammer here, so I'll switch to that flow graph, we'll see that it's now classifying the signals as 1. So we can see here now all of these are being classified as 1, so it's detecting this as CNS. It hasn't lost its ability to classify these old jamming types. And if I switch the gain down, it can still classify norm. We can actually add another class. We have a third jamming type, the RES, the reactive spot jammer. And I'll switch over to that flow graph here in a second. So this is the flow graph for the RES jammer. To implement this, we actually had to implement a custom block. Noted here the RES jammer _ custom block. The way that this works is it takes an FFT input and does energy detection based on it. So it'll take a 128-point FFT and calculate the squared magnitude of this. And if the squared magnitude goes above the specified threshold here, it'll switch into jamming mode. Now it gets these samples from the jammer's receiver, called the jammer sensor, and takes the FFT on that. So once the jammer's receiver picks up that there's some signal present in this band, then it will start transmitting briefly. And then it'll stop, detect again, is there still somebody trying to transmit? Jam again. So if I run this flow graph now, the classifier in our terminal will once again detect that a new jammer is present, and it'll switch to collecting 100 frames again. So while that's collecting, we can take a look at our receiver here. So we can see this jammer reacting here, that there's no signal present. All of a sudden a signal comes on, and a brief moment later, the res jammer activates and jams briefly. And once there's no signal present anymore, it stops. So we've collected all 100 frames, and in our terminal, we're starting to train again. This is actually going to train for longer than our previous training session. Every time we add a class to this, we need to train for even longer because it's now more difficult to learn on this new class. It takes just a little bit longer. So in this case, we just doubled the number of epochs. The actual value here, we didn't play around too much to see how fast we can get this training, but still 160 epochs does not take that long on this level of data. So you can see we're already over halfway through this training process. So in a moment, this training will be finished, and we'll be able to see this classifying the res jammer as class 3. So this will be the 4th class. And just about finished. So there we go. We have jammer classified as 3. So it doesn't label it, but it knows it is a different jammer.
Some of the key accomplishments were that we were able to classify jammers, were able to synchronize a machine learning section with the USRP, receiving in real time. So right as the signal is received, the machine learning part classified the signal, leveraged incremental learning so that online and supervised learning could be done. The classifier was able to adapt to a changing environment, so new jammer types were learned as they were observed, and the progress made was enough to justify future research into intelligent receivers.
We experienced several challenges in both hardware and software in this project. In hardware, it was challenging to make the reactive jammer responsive enough for real-time jamming. We had to push the USRP hardware to its limits when receiving samples and responding in a reasonable amount of time. We also had to limit the jamming types implemented to stay within the constrained category due to the limited number of channels. If we had at least 2 more channels, we could have implemented more complex jammers, such as TCP ACK packet jamming and network packet spoofing. In software, we originally used the incremental learning architecture implemented in the paper Large-Scale Incremental Learning. This architecture was designed using ImageNet, which was not very suitable for our application, and it further used out-of-date software. We had to make our own implementation of an incremental learning architecture using up-to-date software.
We learned how to configure the USRPs to synchronize multiple transmitters and receivers in a single band, and made a custom GNU radio block in C++ to decrease jammer response time. To implement more complex functions such as machine learning and the RAS jammer, ZMQ sockets were used to add Python scripts outside of the GNU radio flow graph. This allowed us to synchronize GNU radio and the USRPs with machine learning algorithms. We published the results of the Supervised Incremental Learning Jammer Classifier at the SPIE Defense and Commercial Sensing Conference. We furthered this work to include online, unsupervised incremental learning, which could be further published.
For the future work, we would like to expand the incremental learning architecture for use as a public library resource, implement the online learning in embedded systems, and be able to tell the difference between known and unknown jamming types before learning to classify a jamming type.